Okay, yeah, I hope you can hear me. Yes, I have to admit that I will provide more of a physics-oriented presentation, but I did take care of looking up some numbers for HPC, because this is, at the end of the day, an HPC meeting. So my goal is to show you what we're doing at KU Leuven in the context of plasma astrophysics simulations, which have leveraged HPC systems of Belgium and beyond for quite a long time at this point. We rely entirely on HPC systems, so I hope to show you how important it is to get support from HPC systems for the kind of simulations that we work on, not just me, but our whole section at KU Leuven and beyond. And so just to give you an idea of who I am, I'm a professor at KU Leuven and at the Center for Mathematical Plasma Astrophysics, Department of Mathematics, but I'm also at the same time a research scientist at the Royal Belgian Institute for Space Aeronomy in the FED Twin program that some of you may be familiar with. At KU Leuven I do most of my work actually. I have quite some people in my group, mainly students and also postdocs. And, well, okay, I've been around the world a bit as a postdoc and student, but the most important piece of this slide is that I do research on plasma astrophysics, both in the solar context and in the high energy limit. So we're talking about plasmas around the Earth, as well as plasmas around black holes and neutron stars. I also deal with high performance computing, meaning that I use it and hopefully also develop numerical methods and codes that leverage the HPC systems we have. So for whoever doesn't know what a plasma is, this is a recap slide that I think you've seen in primary school at this point in time. I'm pretty sure that everybody in this room at least has heard of plasma once. But if you didn't, then just know that plasma is this fourth state of matter that, or that's how it's marketed typically, that is basically a gas of charged particles, right? And the interesting bit is that, as you may or may not know, the universe is 99% made of the matter in the universe is 99% in the state of plasma. So it's kind of important on a global scale to understand how plasmas work, behave, etc. Plasmas are found on Earth and in space, and in space, which is mostly what I deal with, you can just think of basically everything you know aside from planets as being made of plasma, really. So the sun is a giant ball of plasma, the Earth is surrounded by plasma, and then essentially each and every galaxy is practically made of only plasma. And black holes and neutron stars are surrounded by plasma. In the context of solar physics, sorry, this keeps happening every time I give this presentation. In the context of solar plasmas, the most important thing that we maybe want to study is the fact that the sun, being a giant ball of plasma, releases a lot of plasma in the heliosphere, in the region around it. And this plasma, well, you see here some solar explosions that you may have seen in the news also. These explosions are, as you see from this picture, actually many, many times the size of the whole sun, and they can reach Earth and interact very strongly with the Earth's magnetic field, to the point that we can get serious disturbances in our technology. We can get satellites being disrupted. We can get hazards to astronauts, as well as interruption of power grids even on the ground. So it's kind of important to run simulations to understand how plasma dynamics works, because if we can understand how they work, how these explosions work, for example, we can, for example, take countermeasures, which means maybe turning off our power grid before it gets destroyed. You see here an animation of how the magnetic field of the Earth looks like. It's a dipole, and what you see here is a bit of a model of how this dipole, which you see is already stretched in one direction, is modified by the interaction with solar plasma. You see here that a big explosion came from the sun, and it's heavily impacting the structure of the dipole magnetic field around the Earth. This, what you see here is already a simulation. And this is a model that allows us to understand a little bit how exactly the plasma that's coming from the sun interacts with our own magnetosphere, and potentially what it means when there is a big solar explosion that's coming towards us, in terms of how much we can expect it to be interacting with our own systems, right? Could go on, but I think you get the picture. And Yes. One doesn't need to restrict themselves to the near-Earth environment. You can take this plasma dynamics to be important even, as I said, beyond the Earth, in fact, in the whole universe. I hope you can see this. It's a bit too much light, but there's something that happened a few years ago, is that you may, I'm sure you actually heard it in the news, there's a bunch of, let's say, a couple hundred scientists that got together, pointed a telescope to galaxy M87 in the sky, and for the first time, with the most precise telescope, they obtained this picture here that I'm sure you've seen in 2019. This was marketed as the first picture of a black hole, right? You must have heard this, just like everybody did. Now, if you have never studied black holes, that's fine. But one thing you know about black holes is that they are black, and therefore you can't see them. So what is it that you're actually seeing in this picture? It's not a black hole. It is light, but light can't come from the black hole. Therefore, where is it coming from? Well, that can only be matter that's emitting light. In other words, a plasma under very extreme conditions, in fact, highly relativistic conditions, that's emitting light due to some quantum dynamic processes. And the black hole in this picture, well, you can see it, but it will be somewhere like in the middle, right, of the donut. So whenever now you hear that this is the first picture of black hole, you're going to rise up your hand and say, no, actually, this is the first picture of the plasma around the black hole, right? And we need to understand it, because this plasma is the only source of information we have about black holes themselves. They are black. We can't study them unless we study the plasma around them. And if we understand that dynamics, we will understand how the black hole behaves. Okay, so plasma is interesting. I think I already pushed that message beyond astrophysics. You can also think about fusion, propulsion, torches, applications. So there's wider interest in what I'm showing you. Also can make beautiful visuals like what you see here on the right in terms of simulations we run. One thing I want to highlight, however, is that well, I'm just going to go with the animations, is that when you think of plasmas that exist in these astrophysical systems, then you think of plasmas that exist on scales which are unimaginable. If you take galaxy M87 that I was pointing at before, there will be the dot on the top left of this picture. That's a whole galaxy. And then there's a ultra-relativistic jet of plasma that comes from it, and that jet may be living on scales of around 10,000 light years. But the black hole itself that I showed you before has let's say, a disk of plasma around it that may be something like 40 billion kilometers. There's already a gigantic difference in scales between the jet itself and the black hole, where the jet is launched. And then if you could zoom in into the plasma around the black hole itself, you would see some turbulent mass that is ultimately composed of plasma particles, like basically electrons and protons, which live on a dynamical scale of, let's say, 1 kilometer. How can you capture 10,000 light years down to 1 kilometer in one single model? It's kind of impossible, right? We have to make compromises. We study plasma physics with theory, experiments, and observations. What I focus on is theory, and when it comes down to theory, you can do pen and paper calculations or simulations, which is what I do. And then you need to do analysis on these simulations, right? Now, simulations, you already understand, they have to be massive simulations because you're studying systems which are in principle gigantic. So you need supercomputing. Okay, so I want to stress this fact, right? We need supercomputing facilities. It's usually the average size of a simulation that we're looking at has order billions or tens of billions of numerical cells, or hundreds of billions sometimes. And most likely you don't just need to discretize your equations on a grid, but you also need particles. So you need actually to track individual charged particles through this grid, and then you need, again, order 10 to even maybe 100 billion particles, which need to be tracked for a very long time. So recently we started using GPUs for this and exascale facilities. And we also need, well, on top of being able to run the simulation, we need to analyze it, which sometimes it's only possible actually on supercomputing facilities themselves. In my work, I focus on VSC. Well, I use many clusters around the world, but for the purpose of this talk, I will illustrate what we did on VSC and CSC facilities, so Hortense and predecessors, and LUMI. And I will try to just quickly go through a number of applications we have produced with my group over the last, say, well, few years actually. I could go further back in time, but it doesn't make a lot of sense. And so I think maybe I tried too hard, but I tried to put here 3 axes where you see what kind of scales we're talking about. We can talk about simulations of plasmas on macroscopic down to microscopic scales in the regime that is mostly the fluid regime that will be corresponding to your classical fluid dynamics equation plus electromagnetic fields, so some Navier-Stokes type of equations, if that tells you anything, down to kinetic equations where you actually have to solve for each single particle. And then in terms of energy, you can go from the Newtonian regime, which is proper for, let's say, solar plasma, up to relativistic regimes for black holes and neutron stars. In all these cases, the codes you use change quite a lot. You go from a fluid type code that implements certain specific algorithms to a kinetic type code which involves particles, and then whether it's relativistic or non-relativistic involves physical ingredients, right? Okay, so for low energies, we can what we have focused on is the heliosphere. I already sort of highlighted what the problem or the dangers with the sun are. We need to study the sun and understand, for example, solar explosions. Well, okay, you could actually think of studying the whole environment even around the sun, right? The heliosphere as a whole, but that's very hard. So what we focus on when we study the sun with these methods is usually actually main plasma structures. So we study the sun itself as a ball of plasma, mainly its outer layers called the corona, where certain specific structures exist. I don't know if you can see my mouse. Yes, you can. So for example, if you look at the surface of the sun, you can identify certain specific structures here, such as loops. You can identify explosions launched by the sun. You can see, we actually know that the sun emits a continuous outflow of plasma, which is called the solar wind. And then this is linked to a series of plasma-related phenomena, like coronal mass ejection, the expansion of solar wind, turbulence in the solar wind. All of this contributes eventually to how this plasma will interact with the Earth. Okay, so what did we do in practice? So a few examples. We can run, for example, fluid simulations on the macroscopic scale. You take one of these loops on the solar corona and you make a model of it. It's maybe not a great model, but it is a model. And then you run it dynamically to look at, let's say, the turbulence that develops inside the loop itself. This impacts, in fact, how, for example, charged particles can be accelerated up to very high energies. And these energies are what eventually causes problems for, let's say, satellites or astronauts. So that's important to understand. Now, what is the peculiarity of such a simulation? This is something we do very routinely at KU Leuven with a code that's called MPI AMR VAC, which is an AMR code. So it uses adaptive mesh refinement. It's very highly optimized to run in parallel on supercomputers. And the AMR scalability is pretty good, actually. One typical run of such a code for such a simulation that I'm showing you here is maybe 1 million CPU hours, and this is on the low end of this kind of runs. Right? So we have a few papers to check out. I'm going to try to always sort of link them here if you're interested. But so imagine this is like a simple simulation of one very specific structure on the surface of the sun. To understand it to a decent degree, we need order millions of CPU hours. We can go further. So inside the heliosphere, we can look at coronal mass ejections, these explosions from the sun. We can simulate the whole structure itself, the explosion, but we can also specialize and look at, let's say, smaller sections of the ejection itself. For example, the front of the ejection. You can simulate just that. This would imply using a local model that you can target with, let's say, flow particle simulations. In this case, then we're looking at a shock. You see sample simulation here on the left, a shock that propagates at the front of this explosion. This is a full particle simulation, and it's in fact taking out a very small piece of the front of the explosion. Such a simulation that you see here on the left is already 5 million CPU hours. When you do this, on top of having a very high cost, you also have to start thinking about how exactly you're parallelizing your system, because when you simulate a shock, maybe you're familiar with that, maybe not. But all your particles, if you're simulating particles, all your particles tend to be bunched in very specific regions of the domain. If you look at this animation here on the left, you will see that there is a shock front that's propagating from left to right, let's say, from right to left. Behind the shock, you don't have many particles. In fact, you have 0 particles. And that means that your parallelization is limited by the physical system that you're simulating. If all your particles are, let's say, on the left of the domain, when you parallelize this system, if you put processor from left to right, equally spaced, then you will have a gigantic inefficiency. You will have parallel inefficiency that's very high. So you can only slice the system, for example, horizontally in this case, right? And that limits you, because maybe you don't have, maybe you can only slice so much, and you may want to use more CPUs, but that doesn't make sense. That will only introduce inefficiencies. So this is something we face. So, when you see this number 5 million CPU hours, that also includes the fact that the parallelization itself may be very hard. Another example is what happens at Earth, actually. The Earth has a magnetic field, as I showed you before. This magnetic field is sort of a shield, really, when it comes to interacting with the solar wind plasma. At the edges of the shield, which are, well, they kind of look like this in this cartoon on the left, at these edges, plasmas from inside and outside the magnetosphere of the Earth can mix. This is very interesting to study because this mixing is a way through which particles can penetrate the magnetosphere. We need to study this. In this case, we do this with fluid and/or particle simulations. These simulations are, again, of a very small piece of this system, but we're talking about at least 5 million to 10 million CPU hours. For these simulations, also the important thing is that you need very, very long simulation time, very long physical times. And this implies that maybe your classical particle or fluid method is not enough. You will need to apply a better method that allows you to run for very long times without losing physics. In full particle simulations, classical methods, explicit discretization methods, tend to degrade over time in terms of your solution. So you will introduce errors, for example, in the energy, which accumulate over time, and over very long times your solution is destroyed. So you need to apply better methods, implicit methods, for example. But in that case, parallelization becomes much more difficult. For example, on GPUs, porting a fully implicit field solver is very hard because the memory requirement to do a global implicit solve is very high. And so this introduces additional parallelization problems when it comes to porting your code to newest technologies, right? This is an example of actually a very extreme simulation. This is my student Maximilian, who's trying to simulate a blob of plasma that's expanding in the solar wind. You see, actually, you will see the expansion in these animations. This blob of plasma is both turbulent and expanding at the same time. So these are like two phenomena that happen on very large scales. This is a small piece of plasma, but these are the simulations. These are the biggest simulations that have ever been done, and each of them is at the very least 10 million CPU hours. For one run. Okay, so if you mess it up, it's quite a problem. These are simulations that need to be run for very long times because you're not only simulating the electron and proton physics, but also the expansion and the turbulence over fluid time scales. So we're basically doing a fluid simulation, but with full particle methods. So these are really gigantic runs. When you do these runs, well, the efficiency is super important, right? And now you may say, oh, but you write 10 million CPU hours, but why don't you do this on GPUs? Well, because to do this expansion trick that you're seeing here represented, you need to port the method for the expansion itself to GPUs, and this is not obvious once again. So there's implementation problems, parallelization problems, and also the fact that porting this to newest technologies may not be straightforward. Okay, we can see how much time I'm spending on this. Oh, it's not too bad, not too bad. I can go quickly through other applications. So I will just highlight the fact that when you go to black holes, the problem of black holes is not only that there's very complicated plasma dynamics, but the plasma dynamics mixes with strong gravity. So you need to add general relativity, basically, to your equations, right? And then you can simulate whole black holes, as you see here on the left and right, which is what the collaboration which produced the first pictures of black holes actually did. What you see on the left is the plasma structure on the black hole with like a disk and a jet. And what you see on the right is actually what you would see if you were to observe this with your own eyes. The reason why they differ is that around the black hole you have bending of light due to general relativity, right? And so if you launch a bunch of light rays on straight lines around the black hole, they will curve. And so the picture you get will not be the actual structure of the black hole, but a representation of it that depends on the gravitational distortion. This has been used, as you may have heard, in movies such as Interstellar to create graphical representations of how a black hole would look like. What you see here on the right is the biggest simulation of the whole environment around the black hole ever run. And this was done on GPUs. So we have very efficient GPU codes that can solve the fluid equations and that can run on actually thousands, tens of thousands of GPUs for very long times. And only that made possible to run simulations such as what you see there on the right. The simulation is so large that for the first time people could see not only the disk of plasma around the black hole, but also its fragmentation into multiple subdisks because of the misalignment between the black hole spin and the plasma spin itself. This is very impressive. These simulations that I've also done myself are fluid simulation then. They simulate the whole environment around the black hole. Each of them typically takes at least 30K GPU hours, but at least. So that's sort of a baseline, right? So each of these simulations takes so much resources that a typical allocation on LUMI allows you to run, let's say, 5. And then that's it. But these are the biggest simulations ever done, and they are absolutely necessary. What you see here on the left is a black hole. What you see there, the bottom right, is a neutron star. These simulations are the next step in understanding what happens in extreme astrophysical environments. You can also do the other approach that I showed you also before. You can extract little pieces of the accretion disk, for example, of the disk of plasma around the black hole, and run local simulations, right? Now, these local simulations are, once again, simulations that are at the full particle scale, but need to be upscaled up to fluid system sizes. So these are, again, gigantic simulations of maybe 50 billion particles and billions of cells that need to be run for fluid time, so for extremely long times. Each run maybe takes 20 million CPU hours. Once again, porting these simulations to GPUs is very non-trivial because of exactly the numerical methods that you're using. In this case, it's very hard to explain it in a short time, but the simulation you see on the right has very, very special boundary conditions between the left and the right face. And these boundary conditions are such that the MPI topology changes over time. So that's not great, because it means that you should, for full particle simulation, you have to remap your particle communications all the time. That's hard to do on GPUs. Possible, but hard. I can go on. I think I'm sort of running out of time, so I can highlight a couple more things, and that's it. Just so to give you another idea, we can run simulations of turbulence. We can run simulations of what we call magnetic reconnection around the disk of plasma of a black hole. These are also extremely large-scale runs, and then can take up to, from let's say, 10 million CPU hours, 3K GPU hours each run. You can do these things in 2D and 3D, and now in 3D especially we are seeing the benefits of using GPU codes. These runs that I'm showing you here are both CPU and GPU, order 5 million to 3 to 5, 10K GPU hours per run. I think this is my last simulation slide. Then you can obtain things like what you see there on the top left, which is one of the largest simulations of turbulence in these plasmas ever conducted, which was only possible with GPU. Right? And in this case, that was actually possible. But this simulation that you see on the top left is already, I think, 5K. And what you see here on the bottom right is a simulation of a neutron star, of the whole environment around the neutron star, and that's at least 30K GPU hours. These simulations would actually be impossible on CPUs. Okay, just because I think I talked about physics too much, I just want to highlight some HPC numbers. We have mainly used, as I said, VSE and CSC facilities for the things I showed you here. The codes we have scale very well, in fact, on these facilities. We have now actively, we are developing actively, let's say 6, 7 codes that are deployed on VSE and CSC infrastructures. Most of these codes are CPU based, but we have at least 2 very high performing GPU codes that are that are very good for these specific architectures. As I highlighted a few times, moving to GPUs is not always entirely possible. So, doing the step of porting may require resources that we maybe don't have. We may require a full team of professional coders who dedicate themselves to that. I'm interested in talking about it, but we don't have it. And I also want to highlight that we have a Center of Excellence funded by the EU through the Euro HPC programs that you may have heard of. This COE is called SPACE. There are a few currently running. There are, and a couple of them are actually based on plasma stuff. Ours is called SPACE, and its intention is actually to port one of these codes to GPUs, which has been done. Okay, I think I don't need to repeat what I'm showing you here in my summary. Plasmas are interesting, and HPC power is absolutely needed. If you're interested in knowing more, yeah, I'm here, happy to discuss. But in the meantime, thank you very much to the VSE and CSE people for granting us all the resources they do, because they are absolutely essential. And effectively, you need them to advance the state of the art.
Any questions?
Yes.
Is it possible to classify the dynamics of plasma which arrives to Earth?
What do you mean classify?
Yeah, I mean is it the dynamics close to Earth depends on the place or the explosion or the type of the explosion?
Yeah, very good. Of course, that's exactly right. One of the problems we have is that plasmas don't forget about their initial state, right? And so when they're emitted at the sun, you should in principle follow them through their whole evolution until they get to the Earth to get a good initial state for your simulation, right? But that's impossible. That's just not possible, at least to the level of detail that I was talking about when I talk about particle simulation. You can't do that. It is possible in MHD simulation, and so something I didn't explain, but that is certainly possible and actually pursued, is to run fluid simulations that actually can capture, let's say, the global scale from the sun to the Earth, and then try to extract, let's say, a smaller piece of that simulation to be used as an initial condition for full particle runs. This has been done, is being done also by my colleagues in Leuven. I mean, we have several projects on this specifically, and we have a model for full fluid simulations of the whole heliosphere, which includes AMR. I can elaborate, but yeah, that's sort of the global picture of our section as a whole. Yes.
Okay, so thank you again.
Thank you.